that we had from last time. The first question, I have three written down here. The first was about the time of the shower development in the calorimeter. So if you think about the electromagnetic shower development, for example, the one that had everything to do with synchrotron, well, bremsstrahlung, radiation, and pair production. The question was how fast that happens. That basically happens instantaneously. If you think of bremsstrahlung as being nothing more than just the interaction, electromagnetic interaction of the charged particle, the electron in this case, with a nearby nucleus, then that happens instantaneously. The thing we should be worried about, though, is how fast the information gets read out from the detector. So let me give you two examples here. So we said last time that in CMS, basically the particle comes in and there's a shower that takes place entirely inside this crystal, this homogeneous calorimeter, right? So the shower develops right away. Eventually it comes back down, so you have the blob in here. The question here is how fast the relaxation time is for the scintillator. That's the lead tungstate crystal for CMS. So this lead tungstate crystal has some scintillator, and I guess you know that the scintillation is nothing more or less than just promoting the electron up to another energy level, waiting for it to fall back down and release the energy as a photon that can be read out by the photomultiplier or whatever is at the end of the crystal. So the CMS work that's been done says that in the first 50 nanoseconds, so the amount of light that's read out in the first 50 nanoseconds divided by the total amount integrated in a microsecond, which is basically a very long time, is around something like 80%. So it tells you that the photons come out right away within the first 50 nanoseconds. Keep in mind that the bunch crossing time is about 25 nanoseconds. So we don't have a real measurement of how fast exactly the scintillation happens, but we do know that almost all of it happens in the first 50 nanoseconds. So for all practical purposes, that's on a physics timescale fast, but not quite fast enough for the LHC because you know that you have 25 nanosecond bunch crossing time. So the thing that saves you is that the showers are happening and they're spaced out according to their 25 nanoseconds between collisions. So you have one shower, let's say two showers happen to go into the same crystal. If they happen to go into the same crystal, then you would have to be a little bit worried about scintillation. You'd have to be a little bit worried about the showers interfering with each other and the scintillation light from one shower being counted in another shower. But the fact that this 50 nanoseconds happens even if it did happen at a longer time scale than the bunch crossing 25 nanoseconds, it's still not a problem because it's unlikely that you'll have electromagnetic showers in consecutive collisions. In fact, it's frankly unlikely that you'll have anything interesting in consecutive collisions, which is what we were talking about with the cross sections from MAP. So that's not really a big worry. In Atlas, where the calorimeter is an absorbing calorimeter, so there's a sheet of lead followed by an active chamber, and this active chamber is a gap that's filled with liquid argon. The liquid argon is ionized, and then the ionization charges drift to the edges of the gap under some applied E field. So that's pretty much the same as the solid state detectors that we were looking at. In this case, the gap on either side of the electrode, actually it's a gap with an electrode in the middle, is about a 2 millimeter gap. And it turns out that the drift time for the ions to drift to the electrode is something like 400 nanoseconds, less than 400 nanoseconds. So that time actually determines how thick you want this gap to be. I mean, on one hand, it's inefficient to have a gap that's very small because then you have to have a lot of gaps. But you don't want to have a gap that's much larger than 2 millimeters because then the readout time would be longer than this 400 nanoseconds. Okay, that was the first question about the timing there. But the physics shower itself is basically much faster than either of these readout considerations. The other question was about the shape of the beta block distribution. You remember seeing something like this, where this part is called the relativistic rise. And I had given you the DEDX, and I said the DEDX actually has some log terms in here, and I just wrote them like this. It actually turns out that the arguments inside the log terms actually look something like beta squared, gamma squared. So even though what was in this constant of proportionality didn't have any gamma, it only had beta, And essentially, once you get up here in this regime, you're already at beta about equal to 1. This relativistic rise here comes from this log of gamma squared dependence. Okay, that's not the physics answer, but that's what's missing from the equation that I wrote on the slides before. Okay, but someone was right. For all practical purposes, once you get up here, the difference, because it's just a logarithm of gamma squared, is not very large between the different particle species. So you don't really have particle ID separation for those. The third question was about the force. We talked about the force that was the QV cross B, or just QCB. But someone pointed out that there should be another force, which is the QE, which is wherever a charged particle comes close to this strong electric field. I said the electric field was strong near the wire. And so thanks to the people that hung around afterwards, we kind of worked out what would happen here. If the electric field is on the order of hundreds of volts, or the potential that creates the electric field is on the order of hundreds of volts, what you have here is something like 100 EV. Okay, so the 100 EV has to be multiplied by some time, basically, to give the change in the energy, but that's the order of magnitude, okay? So the order of magnitude here is something like a change in energy of 100 of EV at the worst, right? That would be at the worst where it feels all the effects from the electric field. And that's very small compared to the momenta that we're talking about for the particles, so not really an issue there. Okay, so those are good questions, and I hope that answers some of them. Whoever wants to know a little bit more about beta block, maybe we can talk a little bit more about the physics reasons for it. Okay, today I'm going to talk about hadronic jet physics. You had the introduction this morning from the theory side from Matt Strassler, and he basically set things up explaining how we have this duality between the partons and the jets. So from my point of view, the partons are what you would use in the calculation, but the jets are real. That is, the jets are what we really see in the experiment, and the partons is what we choose to use in the theory to try to explain what's happening at the matrix element level. I even changed my line here because I learned from Matt this morning. Is Matt here? I had something about lambda QCD for the jets, and as he pointed out this morning, the jets really have nothing to do with hadronization. They have everything to do with the radiation. I call it radiation. Other people would call it showers. And then the hadronization is essentially transparent for all these particles going through. Okay. From the point of view of experiment, he mentioned that the reason to even look at jets is that the jets are a good proxy for what's happening in the matrix element. So if I see something like this, I have a good idea that this really comes from two gluons in the final state. So here's my initial state at LHC, two gluons. So a dijet event like this looks like two gluons in the final state, or it could possibly even be two quarks in the final state. And what we do is we'll often talk interchangeably about the partons and the jets, but there's not necessarily a one-to-one relationship between the two. For example, you could imagine having a gluon emitted here from this quark leg, or in fact even from one of these gluon legs up here. And if these are close together, what you'll see sprays of particles that are close to each other, and it's very difficult for us to tell experimentally whether this should be one jet or whether this should be two jets. So I'll spend quite a bit of time today talking about how we determine how many jets are here and how we cluster the hadrons that we see in the detector into jets that are somehow proxies for the partons. And in fact, if you talk to some experimentalists, they'll say, all we care about are jets. We don't really care about the partons. And that is true maybe strictly from the QCD measurement point of view. But the other reason we like jets is that if we were to draw some sort of supersymmetric or even, let's say, searches, in fact, let's just say, we have a Higgs, and the Higgs goes to BB bar. What do we see? We don't really see the B quarks, as Matt said this morning. What we'll really see in the detector is we'll see some jet of particles. And by measuring those jets of particles, we will be able to say something about the Higgs. So in other words, the jets are our experimental proxy for the partons, if you want to think of it that way. So it kind of works both ways. You use the parton model to describe what you see in the experiment, but from the experimental point of view, we use that fact to try to predict what we'll see in the detector. So when you think about B quarks coming off of top, that means a B jet for us. So we'll say more about that. And historically, experimentalists have really taken this one-to-one relationship, at least in the past few years, a little bit literally, but people are becoming pretty savvy about trying to understand from the theory point of view what it really means to have a jet, how jets might be merged in the theory, what merged jets look like at the parton level, and things like that. So this is a place of good working relationship between theory and experiment. Okay. So what I'll talk about for the next few minutes is how we actually cluster the particles that we see in the detector. You remember last time we did all the discussion about how we see the different particles in the detector. The charged pions, the pi zeros, the protons, the kaons, any of these things that come from the jet hadronization. Okay, so the hadrons that come out of the jet. And what I'd like to talk about today is how we go from those particles that look something like this in our calorimeter. And if we look at the unrolled version of the calorimeter that you saw this morning, if you have phi and eta, basically each one of these particles in the ideal detector situation would look like a little blob in the unrolled calorimeter. So what's the way that we can try to cluster these particles together in a meaningful and theoretically motivated way to give us jets? That's the real question. Keeping in mind, by the way, that there will be other particles, soft particles, that are scattered throughout the detector because of the underlying event. Actually, while I'm at it, and because it will be useful for what we have to say, let's go to the dictionary that you have on the last page of the slides, just to make sure we're on the same page here. There were some questions about pile-up this morning, so let's discuss those right now. So I find this dictionary to be very handy just to make sure that everyone means exactly the same thing whenever they're talking about these underlying event and pile-up. So for us, what it means, we have the hard scatter, and the hard scatter is the bit that looks something like this. So the hard scatter is what you would usually think of if you're thinking of maybe a 2-to-2 process. Okay, so this would be the outgoing partons, these two gluons. This is what you could think of as the hard scatter. Where do these gluons come from? Well, the gluons come in some way from the protons, and I'll just draw the protons as these three quarks moving like this, the other proton as these three quarks moving like that. Okay, so roughly speaking, we're looking at a bigger picture than just our parton level diagram. We're actually acknowledging that these gluons are coming from protons themselves. So that's what we call the primary hard parton-parton scattering. So these are two partons that are in specific protons in the two bunches that are colliding in the collider. So this also includes the initial state radiation, or is very closely related to the initial state radiation, where I define that as being the radiation off one of these incoming parton legs. Okay, that's the ISR. So in addition to that, we have the underlying event. The underlying event, the key here is the underlying event really is the stuff that happens between the partons that are interacting here. So in other words, let me say what I mean here. So if you think of these gluons, for example, as somehow, well, actually, let me take these gluons here. So these gluons in the final state here. So these gluons are actually could have some string stretched between them, if you want to think about it that way. And this is the part that might be producing some extra hadrons. Okay, so these extra hadrons are coming out like that. This is not really a formal Feynman diagram, but I'm just trying to give you a feel for what's happening here. So you have your jets that are coming off from these gluons. Okay, this is basically making a jet. But then you have other soft particles that are being produced somewhere not around the jet necessarily. So the jets might be these two sprays of particles, and then the soft particles that are coming off the string might be scattered throughout the detector like that. So as far as we know, this underlying event is basically uniform, at least when it's not near the jet. So as long as you're not near the jet itself, it's uniformly scattered throughout the detector, for sure in phi, maybe not in eta, but for sure in phi. And so this is one part of what we call the underlying event generically. You can see everything in yellow there is that underlying event. So what it is it's the multiple perturbative interactions, multiple parton-parton interactions, which I didn't say yet, could be other partons that are inside the proton, the same proton, interacting themselves. Okay, so this would be another interaction, soft interaction probably, because you're unlikely to have two hard interactions. So it gets to be kind of messy, as you can see. But there's no reason why you can't have some, or it turns out that there are some soft interactions between the different partons in the same proton. Okay. The stuff outside of that is what we call the pileup. So the pileup is really the fact that inside the bunch of protons, so let's say this is one bunch of protons, kind of looking like a cluster of grapes, I guess. And here's the other bunch. These bunches are moving towards each other. And in fact, when you have the collision, it may be that these two protons collide, but there's no reason a priori that these two protons couldn't collide at the same time. So if you have enough protons stuffed into the bunch, taking into account the cross-section for some interaction to happen between the two protons, then you can get pileup. Now, one thing that saves you, I guess I've drawn these bunches a little bit wrong, sorry about that. The bunches actually are much longer than they are tall and wide. So they're very narrow and short from side to side and top to bottom, but they have some bunch length. And this bunch length, you'll remember from last time, has to do with the longitudinal admittance, as opposed to the width, which has to do with the transverse admittance. So even though the beam width is something like tens of microns, dozens of microns, the beam length is something on the order of, let's say, 5 to 10 centimeters. Okay, so that bunch length can be like that. So what it means is that you might have this proton and this proton interact right here, but then you might have this proton and this proton interact as the bunches cross. So what you would see in that case is you would see, if this is along the beam line, you would see a collision happen here. You might see another collision happen here, separated by a few centimeters. Okay, so order of centimeter separation, maybe another pileup event there. This is what we call the pileup. So again, I have to emphasize that the pileup is something that's potentially separated in Z along the beam line because of the bunch length, whereas the underlying event is really coming from the same primary vertex. And Matt alluded to that this morning. So that's the important distinction between the two. And that's why really the underlying event is pernicious in its own way, because it makes it hard for us to separate the things that are coming from the primary vertex. Are they all coming from the hard scatter that we're looking at, or is it some of it coming from the soft QCD? The pileup, while there's more of it, we can have up to 19 events pileup at the LHC, is a little bit easier to try to disentangle, because, like I said, each one of these primary vertices represents a separate pileup event. So in principle, all you have to do is make sure all the particles are coming from the same vertex. Okay, and let's go back. Unless there are any questions about this right now. But I find this to be a handy reference. I hope you will too. Okay, so let's go to fragmentation here. So as far as the jet clustering goes, what we're essentially trying to do, if you think about it, is we're trying to work backwards from the parton shower. Now, we didn't get a full description of parton shower this morning. Are you going to do it tomorrow? Tomorrow, okay. But suffice it to say that what's happening is you have this parton shower that's a quark emitting QCD radiation, gluons, which then can split into more quarks. So that's kind of the rough idea of the shower. It's basically a one-to-many, that's why it's called a shower. So one parton to many hadronic particles. What we're trying to do experimentally is try to work backwards in that. If we're trying to recover this jet-parton duality, what we'd like to do is we'd like to reverse the parton shower in some way. So our way of reversing it is going to be to cluster these particles together. Now, there are 3 different parts for the clustering algorithm that you should consider. And whenever someone is talking to you about jets or measurements with jets, you'd like to consider how exactly these jets are clustered. So the first is what particles are being clustered. It turns out that a useful jet algorithm is one that can cluster not only calorimeter cells that are found in the detector that have some characteristic eta, phi, and E, as Matt said this morning, but can also cluster truth particles. And these truth particles can, again, have eta, phi, and E. Okay, so a useful jet algorithm will be one that can be applied to either the detector level cells or the truth level particles, and hopefully give you similar meaningful answers. Okay. Yes.
What is truth level particle?
Truth level particle. Great. Thanks for reminding me. So a truth level particle means really a hadron. Okay. So I'm used to thinking of these Monte Carlo generators that Matt was talking about this morning, the ones that do the calculation at parton level and then apply the parton shower to give a final state of hadronic particles. So that can actually be done at a theoretical level, and we call that the truth. The reason we call it the truth is that the idea is those are the particles that are going into the detector. Then, because of detector resolution, you have some smearing that has to somehow, may or may not give you all the particles. You may or may not see all the particles. But this is kind of what your best guess would be coming out of the Monte Carlo generator. That's a good question. I use the jargon on that. So let me say truth, and I'm going to say hadron level here. Okay. Because you have to realize what we really measure in the experiment are not the individual hadrons. It would be great, and we're trying to make it so that each individual hadron will leave one blob in the calorimeter. But historically, that hasn't been the case. And in fact, in Atlas now, our best guess is that we might have 1.6 blobs on average per hadron going in. Okay, so that's why I mentioned what we're really clustering are the calorimeter deposits, the blobs. They are a good proxy to the particles, but in order to really make this work, you want to make sure that the algorithms can be equally applied to the hadrons and to the cells. So let me write this specifically, calorimeter cell. Okay, so that's one important thing. The other important thing is which particles should be combined. So by which particles, I mean here's a list of particles with certain eta phi energy values. How do you decide which ones go into the jet? You may look by eye and you may say, aha, these seem to kind of cluster together. These seem to kind of cluster together. I'll call those jets. Well, that's the right idea, but can we make it a little more formal, a little more quantitative? And that's exactly what we'll be trying to do. Okay. The last one, how should the particle form momentum be combined, is a formal question. People did not always necessarily agree on that, but I think now people have agreed to just take what is the seemingly obvious choice of how to combine particles, which is to add the form momentum. Okay. You might think it's obvious, but that was not always obvious. Okay, let me say 2 words about the last line here, and Matt may say more about it tomorrow too. One of the main criteria for these jet algorithms is that they give you the same answer whether or not you have these sloppy particles, these extra blobs in the experiment. So let me show you what I mean. What if I were to say, okay, this is the event that I see. Let me add a little bit of extra particles in here, maybe like this, like this, like this. Okay. So when I've added these extra particles, even if they're very soft particles, you might be thinking, aha, it's no longer 2 jets that are separated. Maybe this whole thing is one big jet like this. Okay. Just to be a little more specific here, what if you have a jet of particles that looks like this and a jet of particles like this, and those are well enough separated that you can see what's happening? What if I put another soft particle, could be a soft gluon, let me draw a little soft gluon in here, right in the middle. If that soft gluon confuses you to make it all one big jet instead of what was 2 jets before, then that algorithm is not what we call infrared safe. So infrared safe means even a soft particle that's put in between 2 jets will cause them to move together. So infrared safe means that won't happen. Infrared safe means you will still recover 2 individual jets, even in the presence of soft particles that are making things difficult for you. Okay. Collinear is something along the same lines, but collinear here means that you should get the same result whether or not you have one single track like that, single particle, or 2 particles that have half the energy but the same direction. So in other words, the total amount of energy in here, not the individual particle count, should really make the difference. Okay. So collinear formally means that you have 2 of these particles that have basically the same momentum. Okay. Yes?
These terms have a theory side too. Does this statement apply to both? Or is this
Which terms exactly do you mean? The collinear and infrared? Yes. I mean, infrared in this case really does mean infrared low energy. And collinear in this case means same.
It's really the safe.
Oh.
It really is the same, and it's really more of a theoretical consideration than experimental one
Right.
at this point. But yeah,
Well, it becomes.
we'll talk about that a little bit.
Well,
Right.
but it may be being used in two senses here.
No, it's the same. It's the same sense. Really, it's an equally important consideration on both sides, because on the theory side, you like to make sure that if you have some extra soft radiation, which you do, that it won't affect your jet-parton duality. And on the experimental side, you'd like to make sure that if you have little blobs that may even be detector effects, that it won't mess up the jet counting.
No, I think that's really not a question. Are any of the algorithms things that you're applying at the level of the trigger, or are these all things that are happening? Are there any triggering decisions that are made using jet algorithms?
Very rough, and then I'll talk about that. So basically, the trigger does not have a lot of time to figure things out. We'll get to the trigger at the end. All it can basically say is, did I have a large deposit of energy in this region? That's all it's looking for. It's not necessarily counting jets or looking for separated jets. It won't deal in the subtleties that we'll be talking about here. Okay. So the first thing that you might try, the simplest thing, and the one which experimentalists have been favoring for the past 5 to 10 years, was a simple cone algorithm. So why do I call it the cone algorithm? Well, in the A to phi plane, as it's unrolled for the calorimeter, the cone algorithm corresponds to a circle in the A to phi space. So it's a circle in the A to phi space with a radius that's equal to some delta phi squared plus delta eta squared. Okay, I should say delta eta squared, delta phi squared. Okay, so basically it's just saying this is the radius of the cone. It's called the cone because if you re-roll the detector up and look at it like this, it'll be a cone in space because the apex must be at the interaction point, must be at the primary vertex. Okay, so in 3D space, it looks like a cone unrolled onto this pseudo-rapidity azimuthal angle space. It looks like a circle. So this is convenient because you say, wow, I know that I always will have a circle when I'm talking about a jet. And the only thing that's important here is how to figure out which particles go in the circle and where the circle lives. So the simplest sort of cone algorithm that you could have is to define some sort of distance metric. In fact, all these jet algorithms I'll be talking about today have these distance metrics. And basically the rule for the jet algorithm is, does the particle, or I should say, is the delta ij, that is the distance between two particles defined with some metric, less than some characteristic value. And let's call this characteristic value r. Okay. If that's the case, then the particle goes into the cone. So you may ask, what are the particles I and j? So the first, we have to start with some particle. We call that the seed particle for this simple cone algorithm. The seed particle in this case is the most energetic particle or cluster that you have in the calorimeter. So what you do is you say, okay, compared to this seed, let me try to figure out if any of these particles have a distance measure, where the distance measure in this case is that simple geometric measure up there, less than some parameter r, less than what I have for r. So if I were talking about a cone jet with r equal 0.4, that means I will pick up all the particles that have an r less than 0.4 relative to the seed jet. Okay, so this is kind of what's drawn here. If something comes outside of that, it won't be included in the jet. This is the question over here. Seed track, thank you. Seed particle, I should say, or seed blob, seed callow cell. Good.
How do you determine what R should be?
How do you determine what R should be? R can be whatever you want, technically. So if you pick an R that's very small, what will happen? If you pick an R that's very small, you'll likely find a small jet here, another small jet here, a small jet here, another small jet here. In other words, you'll end up breaking up what otherwise would be normal jets into a smaller jets, more jets. Okay. So if you picked a very, very large R, you could in principle even pick an R that would be large enough to encompass the whole event. So in fact, this choice of R is a good question. If you have an event where you are looking for something like a dijet, and we know that these dijets are roughly back-to-back in space, you could get away with picking an R that's very large, so an R of 1.0, for example. If you have something like a top quark event, TT bar event, where you're expecting 6 jets, as Matt was talking about this morning, then you could try to figure out, is it likely that these jets will really be separated by an R of 1.0, or should I pick a smaller radius to make sure that I don't somehow cluster my 6 jets all into one? Okay, so this might be your 6-jet top quark event. Okay. If I pick my R too large, I run the risk of putting 2 of these together. And that kind of spoils what we're trying to do with the jet-parton duality, right? So in a case like this, where you only have 2 partons, then it's easy. Now, one rule of thumb you can kind of think about, Matt mentioned this morning, let's say that we have jets that are being measured between 4 and minus 4. Of course, our phi is running from 0 to pi, actually. I always have to think because there's also forward, backwards. It's 2 pi in this case. Good. Okay, so 2 pi. 2 pi times 8 is basically the total units of area that we have in this space here. So you might say that sounds pretty big. So 8 times 6, so roughly somehow 50 units of what you would call eta phi space. Okay. So your 6 jets that you have in there will probably be pretty well separated. But remember that you're talking about an area that's pi r squared. So each one of these jets is going to take up an area in that space of about 3. So you can kind of get some idea of how big the jets can possibly be or what would fill up the space by thinking about how close they are to each other in the phi space. Really the only way to figure out what the right R is to try to do some simulations and try to figure out which one gives you the jet hadron duality that you're looking for, or jet parton duality that you're looking for. So the R, this is a very good question. When you see LHC results, you'll see results that may have 0.4, 1.0, 0.7, and then you'll know exactly why we have all those different jet parameters. Okay, so the cone does have a problem. The problem with the cone is that it's not collinear safe. And why is that? So let's say that we have, and it's drawn up there in the notes too, let's say that you have this sort of jet, or this sort of particle list. So here, pretty obviously, I have one track, which ends up being the seed, or the calorimeter cluster. That's the seed. That's the highest energy one. So we take this as the seed, and we look for the particles in the cone around the seed. Okay, so it may turn out that this particle and this particle are outside the cone, so they're not included in this particular jet. If instead I see what happens if somehow this is broken up into 2 particles, so really this is a little bit of a thought experiment actually, because you have the same amount of energy really, but you've just broken it up arbitrarily into 2 pieces. Okay, so same direction. These 2 together would have added up to make the seed that you had in the first place. So now you can see that you have a completely different seed. Maybe it's this seed over here. You can't quite see which one's longer. Let's say it's this one. So this one will be the new seed, and this will give you a completely different jet. Instead of having the jet that looks like that, you'll have a jet that maybe puts these 2 together, and then everyone else is left out. So this is why the cone is not collinear safe, and this is why it's disfavored now for some of these experimental measurements. So you probably won't see cone measurements at the LHC, and this is why, even though they have an intuitive appeal if you look that way. Okay. Yes?
So I'm just trying to think about what causes the jets to have the particular size they do. So it seems like it'll be set by the differential cross-section of the decays of all the things in the jet. Is there also spreading due to the magnetic field? There is.
So there are 2 different effects. So one is the effect that really is the detector level effect, which is what you just mentioned, something with a magnetic field, something with the resolution in the calorimeter that tells you how big the blobs can be. But as Matt was starting to talk about this morning, there's an intrinsic spread that's due to physics. In other words, you have a parton that has a very well-defined momentum, and then that gets transformed into a shower of hadrons that have some characteristic width. And he actually told us this morning what the width came from, but then I can't remember.
I told you I would tell you tomorrow.
Oh, he told us he would tell us tomorrow. Okay. Good. And I'm not mentioning this today, but the measure of those jet widths is also the complete measure, and then the radial density, that is how it falls off from the jet axis, is one of the most important early measurements of the LHC. So if we don't want the cone algorithm, what can we do instead? There's another class of algorithms that are called the sequential recombination algorithms. And these algorithms are really trying to work back really in exactly the reverse order of what happens in the parton shower. So we'll hear tomorrow that basically in the parton shower, you start from some initial state parton, and basically what's happening is, if I could paraphrase, and Matt will tell me if I'm completely off base here, but you basically have a massive system that ends up losing mass as it radiates. Okay, so where the mass actually comes from, you might talk about tomorrow, but this is the way I think about it anyway. Okay, and what happens at the end is you break down to all the hadrons, and all these hadrons have very little PT relative to each other. Okay, so by the time that you get to the end of the shower, that's what's happened. So what the sequential recombination algorithms try to do is try to put the pieces back together. So let's say we have some showers that look, very roughly like this. This is not necessarily the physics picture, but this will do for the idea. Okay, so what the sequential recombination algorithms try to do is try to take the pieces, the particles, which are closest together. And what we mean by closest together is, again, the definition of the distance metric. So the two main algorithms that you may hear people talk about are the Cambridge-Akin algorithm, and this really does use the distance metric of taking the two which are closest together in space. So let me come back to my calorimeter diagram here. And if I had a bunch of particles like this, a bunch up here like this, I would take the two particles which are closest together in space, so that would be these two particles here. Basically, I have to calculate the Dij for each one of these particle combinations. But these two are closest together. I cluster those two together. And when I cluster those two together, I have a new particle that I've made by combining their four vectors. That's what the recombination part is talking about. The sequential part comes in that next I take the next minimum distance. And the next minimum distance may be two other particles, or the next minimum distance may be that new composite particle that I made in one of these existing particles. Okay, so now they'll be all together in a new recombined particle. And this continues until you've built up all your jets. Technically, it stops whenever the next recombination would be with the beam. So if they get close enough to the beam and there's nothing else nearby, then the jet stops. The jet clustering stops. So the Cambridge-Akin is a very particular distance metric. It's really the geometric distance metric that we talked about. And there are other metrics that you can use. This KT algorithm, for example, has a preference for combining the lowest momentum particles first. And the reason for that is that the lowest momentum particles are typically the ones that are at the end of the shower. They're typically the last splitting, the last step in the shower that you have are two low momentum particles, because by then you're at the end of the shower. Okay. So the idea is that you would take these low momentum particles, cluster them together, and then continue with the recombination that way. So you can see that these two are not necessarily the same. But they are members of the same family of algorithms. So this Dij, this distance metric here, has the same form. In one case, P equals 0, and P equals 0 means it has nothing to do with the KT. By the way, K is what people use for jet algorithms. It really is P. Okay, it's really the PT, but people call it KT. So the important thing there is just the geometric distance, which is that delta Ij. So I guess I really should write in this case the delta Ij now. And the R in this case is the parameter that you've chosen. So for example, I could have KT4. Actually, it's KT.4, but people call it KT4. or a KT7 or a KT10. Okay. So what that means is that you have used the KT algorithm with an R parameter up there of 0.4. So you might expect this to give you a jet that has a characteristic size that's close to that R value, right? It won't be exactly a cone anymore because you're not using only that geometric metric, that geometric distance metric, but it still will be on the order of a size of 0.4. Okay, Nadia had a question up there.
Yeah, but in the stop, so we have some jets that stops only when it hits the beam. But we can imagine that there are really two jets like that, obviously very thin.
Mm-hmm.
Yeah. And the next, in this, you don't stop. If you stop too late, you're in danger of combining them to one jet.
Right. So the thing that saves you is this R parameter, I think. If you have the R parameter be very large, let's see, maybe I'm missing something here, but I don't think so. If the R parameter is very large, then you could, in fact, cluster those jets together and basically have the whole event be one jet. But I haven't said exactly where the R, there's no cutoff in Dij. Okay, that's a good question. What I was thinking is, typically these algorithms define some other value. I've defined the Dij for you. There's another value that we really should consider, which is the Dib. That is the D for some particle with respect to the beam. And then let me bring that back next time, and then we'll be able to see, I think, a little more clearly how it stops before it gets to the beam. Okay. Now there's one possible exponent I didn't mention in this family, and that's -1. So this is a new algorithm, and I think it's a really great example of how there was this interplay between the theory and experiment. This is actually invented by theorists who were thinking about the jet algorithms that experimentalists use and that theorists use, and said, hey, this is a new idea. Okay, so a new idea for a jet algorithm, the first in a while, is saying, let's think about using the -1 exponent. What does that mean? Well, if I go back, let's look at the p=1 exponent. So remember there we were looking at the minimum of the pt squared. We were combining the lowest momentum particles first. So the problem with that is that you could have the lowest momentum particles get clustered together. Let me draw a little jet down here. And somehow forget about the high pt particles. Well, that would actually give you something that would be a very funny shaped jet. Because what would happen is you would be picking up, well, I'll show you in a second what the map looks like of the particles that are included in a jet like that. Let me just say that for the anti-KT, what gets clustered first are the particles with the hardest momentum, with the highest momentum. So in that case, you would say, aha, let me cluster with this very high momentum particle because the 1/k will be very small. So I take the smallest distance ij, and that will be between this particle and this particle. So they'll get clustered together. And then the next one, I mean, it's still doing an angular clustering because it still has that delta ij, which is the geometric part, but that's being weighted basically by the particle momentum, 1/the pt². Okay, so let's see what those look like there. Now this makes both experimentalists and theorists happy, we hope, because for the experimentalists they get a real cone back. And the reason they get a real cone is basically everything's being calculated with respect to this high pt track again. So the first cluster happens with respect to this track, and then you get a combined track or a combined particle that looks like that. And then the next one gets combined with that one again. So basically you're clustering the particles together around this very high pt track. Okay. This is good on the theory side because it still maintains the infrared safety and collinear safety. The reason that does that is that you're no longer looking at, well, let's say you had a seed that was broken down or a high pt track that was broken down into two pieces like that. Okay. So what will end up happening is that eventually those will get combined together and you'll have still the same jet that you would have otherwise. Let me show you what I mean. Okay. So this is a map that shows you the difference in the jet algorithms. So it's exactly the same 2D map that I wrote up here, except it's three-dimensional in that the height, so the z-axis there is the energy of these little cells in the calorimeter. So the energy of those little cells is given by the height of those Lego blocks. And this is called the Lego plot. So if you look at the KT, for example, actually let's look at Cambridge-Aachen first. So you remember this was the KT family algorithm with P equals 0. So it really is using the geometric distance and then doing the combination of the particles. So you can see it's almost a cone, but it's not a very neat, nice cone. Okay? And the reason we'd like it to be a neat, nice cone is that if we have a way of figuring out what the contribution is on average from the underlying event, we could just say, aha, the underlying event has a certain density. Let's say it's a tenth of a GeV per unit in pseudorapidity phi space, in eta phi space. If I know the cone, if I know that each jet has exactly a fixed area on that 2D plane, then I can make a correction on average for the underlying event. If it has an irregular area, like this Cambridge-Aachen, or even worse, like the KT, then it makes it much more difficult for me to do the calibration and remove that underlying event energy. So the best of all possible worlds, we believe now, is this anti-KT algorithm, which gives you almost perfect cones and still maintains that collinear and infrared safety. I should say there's another algorithm called the SIS cone, the stable infrared safe cone, that is obviously giving you cones, but also maintains the infrared safety. And the reason that these anti-KT areas are larger is because it's using R equals 1 versus slightly different parameters for the SIS cone. So I'm not going to talk about the SIS cone. But what you'll see, likely, from the LHC, is you'll see jets that are called something like anti-KT4 or SIS cone 4. And now you know what exactly that means. So you can get different measurements depending on what kind of jets you make. And that's a reflection of the fact that it's not so easy to pick out that jet-parton duality. We may talk about that more tomorrow. Okay, this is the information about how to cluster together into the jets. Are there any questions about that? I'll move on to measuring the jet properties next.
Maybe this is related to that as well, but can you get more information about a jet by looking at the substructure? That's
a great question. The answer absolutely is yes. So what you might do, for example, is you might first try the anti-KT7, okay? So let's say we have a very big jet. And then after that, you might try to break it down and look at the substructure of the jets by using a smaller R parameter. Okay. I'm actually going to talk about that tomorrow because that does turn out to be a very useful technique. But that was only really appreciated, I think, for hadron colliders in the last few years anyway. It was kind of rediscovered. Okay, so let's move on. Yes?
On the cone algorithm, just to avoid any confusion, because the cone algorithm, of course, was used extensively in certain experiments. But as you said, the seeded cone algorithm is collinear and unsafe. On the other hand, that was dealt with by using an unseeded cone algorithm, which is collinear safe and infrared safe. But it's very hard to actually use. So in practice, the way it was used was then infrared unsafe, which then led to the SIS cone to fix that problem. But then anti-KT is so good that whole discussion has kind of mostly disappeared.
I think that may be true. Now, I'm not sure if that's true on CMS or not. I think that's true in Atlas, and I hope it's true in CMS too. Maybe you know. So the comment was that the cone algorithm actually went through several different attempts at fixes. I'll just repeat for the video here. And the first attempt was to try to fix the, what would you say, the collinear safety, right? To make it collinear safe.
I'm even making it more simple.
Okay. And okay, it's a long story. Maybe we'll just leave it at that. We'll move on to measuring the energy. Okay, I said yesterday that the number of particles that you have in the shower gives you an idea of the incident particle energy. So really what that means is that by incoming particle, I don't mean parton, I really do mean hadron. So if this is my calorimeter and I have a pi plus coming in, well, remember the pi plus doesn't deposit because it doesn't Bremsstrahlung in the electromagnetic calorimeter. So we're really looking for deposits in the hadronic calorimeter. So this pi plus actually will do a little nuclear interaction shower here, and this will be a small shower that will be a blob of energy that will give us the energy of the pi plus by itself. Next to the pi plus in the same shower, and these are both coming from the same parton maybe, so let's call that the parton or the quark that's coming in, I may have a kaon, okay? And the kaon comes in, and the kaon makes its own little shower. So if you have a fine enough finely enough segmented calorimeter, you can actually approximate the idea of having one of these calorimeter deposits, energy deposits, which is itself made up of many hadrons in the hadronic shower for every one of the incoming hadrons. So let me specify that here, going from quark to hadrons, we have the parton shower that Matt will talk about tomorrow. And then what we have in here is, I guess, what I would call the hadronic shower. It's happening in the hadronic calorimeter. Okay. So the particles that are actually measured in the calorimeter to measure the energy are all of these. The number of these is proportional to the energy of each one of these incoming particles. Okay, is that pretty clear? In the end, what you get is you get blobs in the calorimeter, and you can measure that this blob is 1 GeV, and this blob is 0.5 GeV. Okay, those are the things that we cluster together. Now, how do we put them together and try to combine all of those blobs together to get a jet energy? And how does that jet energy relate to the original parton energy? That's the real question. If you were looking for example, let's be optimistic and think that you might have something like a Q bar through a Z, and then the Z to, let's say, Q bar again. Okay. You might say, great, no problem. I'll just add up all the energy that I find in the jets that are the quark jets. I'm going to have 2 jets here. And shouldn't I get the Z back? Right? Maybe I should just get the Z back if I add up all the energy that's in the calorimeter. And that turns out not to be the case. So let's talk about why that's the case. Lots of reasons why that's not the case, and they all have to be corrected for in order for us to get back to the true parton energy. I mean, from here, you know that the parton energies that the Z had produced at rest would be 45 GeV, but that's not what we see in the calorimeter. Okay, here are the reasons why. So the first reason is that the particle shower in the hadronic calorimeter has not only hadronic component, but also an electromagnetic component. And why does that happen? Well, if I have a nuclear interaction that's happening inside the hadronic shower, some of these little particles that are produced in here will be pi zeros. And those pi zeros, we learned, will decay immediately to the 2 photons. And these photons will give you a little electromagnetic shower inside the hadronic calorimeter. Remember, there's nothing special about the electromagnetic calorimeter versus the hadronic calorimeter. They're both material. The only difference is that there is just enough material in the electromagnetic calorimeter to make sure that the electrons and photons shower completely, but the other particles don't interact. And a technical way of talking about that is there are few interaction lengths, hadronic interaction lengths in the electromagnetic calorimeter, but there are many interaction lengths in the hadronic calorimeter. So what happens is that inside the shower that's happening inside your calorimeter, you have 2 components happening at the same time. You have an electromagnetic component that's coming from the pi zeros that are created in the nuclear interaction. Sorry, did I say you have a hadronic component? Electromagnetic component coming from the pi zeros. And then you have a hadronic component that is the pions and the kaons and everything else that's produced in the shower, protons, things like that. Okay, so this question of how to disentangle the contributions from the electromagnetic part of the shower from the hadronic part of the shower, you need to disentangle those 2 in order to get the jet energy. And the reason is that you can't predict before how much of the jet is going to have this electromagnetic component. Okay. The next thing is that some of the particles are just absorbed. Both CMS and Atlas have what are called the absorbing calorimeters. I just described them pretty briefly. So the absorber is meant to make sure that the particles interact strongly. So you have a particle coming in, it interacts strongly in here, and then this is the active region that either has some gas or some scintillator that actually counts the number of particles that are coming out of the shower. Okay? So the number of particles are counted here, then there's another absorber. Basically, whenever you have new particles produced in the absorber, if they don't make it to the next scintillation or the next active readout chamber, then they won't be counted. So this is a sandwich of absorber and active material. Okay. And the reason for this is that the active material is not dense enough to create the showers, and the absorber doesn't give you any way to read out the ionization that the particles are creating. Okay. What else? Well, Matt alluded to this morning the fact that the detectors have cracks in them. You might say that's crazy. Why do the detectors have to have cracks in them? Well, something has to carry the data out from the inner part of the detector to the outside, to the trigger and the computers. So there are holes where the cables take data out, and other cables bring power and cooling water in. Okay? Cooling water, cooling gas, things like that. So there are cracks, and if a jet goes into a crack, then the particles that go into the crack are not recorded. So there you lose a little bit of energy right there. I think it's safe to say that basically the energy is always underestimated in the detector, and we have to scale it up to when we calibrate it. Okay, the one exception to that is this last point. The last point will give you extra energy in the jet that doesn't really belong to the parton that the jet is supposed to be dual to. So the examples there are the pileup collisions that I said and the underlying event. So if you have particles from other parton collisions, or other proton-proton collisions, which are the pileup, or the underlying event, which are particles from the same collision, but not the partons that you want to measure, then those will increase your jet energy, and you have to subtract those away. Okay. So for the jet energy, the way that we correct, we go through and try to do all these calibrations, are real benchmarks for trying to figure out what the true jet energy should be. We have basically two big calibration benchmarks. So the first one is the dijet. Looking at the dijets, which are supposed to be back-to-back and give you equal energies in the transverse plane, can help us calibrate for the cracks. So let's say, for example, that in the other view here, we have one jet that comes out through a crack. I draw it here. Typically, the cracks are the edges of the cylinder here because the detector has an end cap that has to close in. Okay. So by looking at a dijet event like this, back-to-back in the transverse plane, we can get some estimate of what the calibration factor should be for jets that are moving into this crack. So that's an eta-dependent correction factor, but this is what we call the relative correction factor. So it just tells you what the calibration constants are of one part of the detector relative to another part of the detector. We also have an absolute calibration, and the absolute calibration assumes that we know exactly the photon scale, the EM scale. And if we see a photon, for example, that's measured in the calorimeter of, let's say, 50 GeV, then we know what the absolute scale must be for the jet on the other side. It should be 50 GeV. Okay. So after we've done the relative calibration to make sure that all parts of the detector are giving the same response after a calibration, then we do this absolute calibration to set the absolute scale of the calorimeter energy. Okay. So we work our way through like that. Someone mentioned that there's also a correction for particles in the B field. You might think that the particles would be equally likely to move out of the B field as to move into the B field. So you might say, aha, no problem, I'll get some tracks that will move in like this. But in fact, because the density of particles is supposed to be much larger in here, you actually have a net flow out. In other words, more of them flow out than flow in. There aren't any magic tracks out here wanting to get into the jet. Okay? They only come from the outside and then get lost outside the cone. Okay. The reason this is important is that this is really a detector effect. So in other words, at production, these particles are really coming from the same parton. They really are part of the parton shower. Where's my parton shower? Okay, so they really are like this. But then what happens is once they get in the B field of the detector, some of them will get swept away. So whenever we take the cone of the particles there, even if it's the anti-KT cone, we'll lose some of those particles because they'll be swept away. Luckily, this is something that we can predict on average and we can correct for with our detailed detector simulation. And I'll say something about that in a second. Okay. The problem is this. You can see that this photon scale will only work up to a certain energy. I mean, at best, we'll get up to the Z scale. So the Z is about 90 GeV. But we really don't have too many data events past that to be able to calibrate these jets up to energies of 500 GeV, let's say. So what we do is we do the best we can with the calibration up to a certain point. That certain point is dependent on how many events we have at that high scale. And then we just extrapolate past that. So when you see these 1 TeV jets, it's fair to ask yourself the question about how well those jets are calibrated, whether the absolute energy that's being quoted is very important or not. Okay. All right. So I'll just say that the systematic uncertainties that we expect on the jet energies are on the order of, let's say, around 10%, 5 to 10%. Maybe eventually getting down to a few percent. And that is the limiting factor on some of these measurements. Because if we say that we are going to require jets above 30 GeV, 30 GeV for the experiment means 30 plus or minus 3. And that can make a big difference in the cross-section that's calculated from the theory. The good news is this, that we take it upon ourselves as experimentalists to correct for all the detector inefficiencies, to correct for the detector resolutions, so that we can correct back to what should be happening at the hadron level. So remember, the hadron level is what's happening here. Actually, what's happening here in the absence of a B field. We even correct for that B field out of cone effect. So what it means is that we are trying to correct back to what happens at the end of the parton shower. So if the theory calculations can also tell us what is supposed to happen or what the models predict will happen at the end of the parton shower, then we can make an apples-to-apples comparison. And that unfolding of the detector is one of our main challenges, but it's something that we have to do to make the comparison with the theory. Now, the other side of the coin there is that it's very helpful for the theory calculations to take things through the parton shower level, through the hadron level, because we really don't have a good way of correcting back to the parton level. We can try, but that's a very model-dependent correction that really should belong on the theory side, frankly. The detector level correction we can do because we have the detector simulated very well. Very quickly, I just have a couple slides on how the detector simulation works. There's an opportunity for further reading, but maybe not in this audience. Suffice it to say that there's a very detailed description of every nut and bolt, I guess we'll be using that phrase a lot this week, in the experiment. I mean, almost literally in some parts. In fact, over here on the left, you can see in the silicon detector, the cables have even been modeled, these little cables that are the pigtails that are curling around there. The supports for the detectors, things like that. Why are they all modeled? Why do we care so much about that? Because the GEONT simulation that we use, this GEONT toolkit, follows each particle millimeter by millimeter, or even at a finer step, 5 microns by 5 microns, or even a finer step than that in some places, through and tries to determine whether the particle has interacted with material each step along the way. So if a particle happens to go near a metal screw or happens to hit a metal screw, it has a higher chance to interact than if it were just going through a carbon fiber module holder. Okay. So these detailed detector simulations are what we use to do the corrections. Luckily, there is a version for theory use too, which is a public version of these detectors. It's basically a parametric simulation saying, if I have a particle that is going in this part of the detector, what will be the measurement that comes out of the detector at that point? Let's say I have a 50 GeV electron. Will that 50 GeV electron be measured as 50 or 48 or 52? These kind of parametric simulations will tell you that. So you can see here some of the examples. The DELFS and PGS, the pretty good simulation, are the two leading products that I know about. So the input is what happens after the parton shower that Matt will talk about tomorrow. The output is what you expect to see in this detector, in this roughly simulated detector. So to give you an example of what's in there, you can see the energy resolution for the electron, the photon. This is really the resolution of the calorimeter. And even the B tagging. So we talked this morning about what efficiencies you might expect for B tagging. It turns out that the DELFS package is assuming that the detectors will have a B tag efficiency of 40% versus a mistag, a light fake rate of 1%. The 1% is what Matt said this morning. The 40 is a little bit lower than what we might have expected. But this can be tuned by hand if you like. Okay, good. Let me say a few words about the unfolding then. Here you can see the effect of the unfolding. And again, this is something that we are doing for the measurements. The Monte Carlo jets is what happens after the parton shower. So that's the parton shower level after the parton shower. So that's in red. What we actually measure are these RICO jets uncorrected, the upside down triangles there. And you can see that there's roughly a factor of 2 that needs to be corrected between those two. So if you were just to take the raw uncorrected results, you'd be off by a factor of 2 in this particular distribution, which is the PT of the leading jet in W plus jet events. So that calibration is something that we do. Okay. Great. All right, let me spend the rest of the time on heavy flavor decay. So some of this I can skip because we talked about it this morning. The key here are comparing the C tau. My C tau are in terms of distances here. So it really is telling you that the C tau for the B quark, without the gamma factor, is about 500 microns, half a millimeter. Now, typically, if you think about what a B jet might be, a B jet coming from a top quark, let's say, is around, very roughly, 50 GeV. So let's say 50 GeV. Since the B quark mass is 5, that's about a gamma of 10. So you could take this C tau, and you could multiply that by a gamma of 10 to get the lab frame typical decay length. Okay? So that lab frame typical decay length would be something like 5 millimeters. That is pretty huge. Okay? Actually, my gamma is probably a little bit high. It might be more like 5 than 10. Okay, 2.5 millimeters. So that's a big difference. Notice that the C tau for the charm is not that much less than the B. So this is why it's a little bit hard to tell the B and the charm apart. All right, here's the key. And this is an important relationship to remember. So Matt mentioned this morning that the significant parameter that we want to measure to make sure that it's a heavy flavor quark jet is that these tracks don't appear to come from the primary vertex. So there's a decay, that's the B meson, or B hadron in general. And then this is the decay of the B. So the two important things here are that the B has some large mass, so it throws these particles off with some transverse boost that basically comes from the mass, or some transverse momentum that comes from the mass. But then also that you have this long decay length here. So this is called decay length. We can either measure the decay length directly, and we do that, or we can measure these impact parameters. So, yes? Question? No. Oh, it's okay. Okay. So the D0 is the impact parameter. If we look at the geometry, which is blown up over here, the decay length in that case is the LB, decay length of the B. So it seems that this decay length is roughly, or the impact parameter is roughly the theta, which is the angle that these tracks make with respect to the jet direction. So actually, let me have the jet direction coming out here and make this the theta of an individual track. And so that, I've written these similarities because I'm being kind of sloppy with the coefficients, but that theta is roughly what the track has for momentum relative to the jet axis perpendicular over its momentum along the jet axis. So that's the P parallel. So the perp and the parallel are relative to the jet axis here, times that LB. So if you carry the whole thing through and you keep track of the gammas, you actually come out to a D0 impact parameter that's the same order as the C tau. So the C tau of the B gives you an idea of how large the impact parameter should be. Now the interesting thing is here, notice that the gammas go away. I said that the decay length would be gamma CT, but the boost is also part of this MB over PB, which tells you about the angle. In other words, the more something is boosted, the longer the decay length will be, but the tighter the spread of the particles might be. Okay, so that's a very rough rule of thumb. So what it means is that really the key thing there is the C tau. Okay. So in the notes, you also have some ideas about how to calculate the primary vertex. We touched on that this morning. Basically, take all the tracks in the event and see where they came from. Okay, so that's where the tracker is very important. And we have a bunch of different ways to tag the jets directly. So one is to use these impact parameters, D0, to calculate the likelihood that each one of these tracks came from the primary vertex. If this D0 is very large compared to the resolution on the D0, that is the D0 over the sigma D0 is large, then you're fairly sure that this track did not come from the primary vertex. And if you have several tracks in the jet that are like that, you multiply together all the likelihoods, and you come up with the total likelihood for the jet. This is the likelihood that the jet came from the primary vertex. Not the probability necessarily that it's a B, but we interpret those as being the same thing. Let me show you. Which direction is the beam? Good. So the beam might be like this. Okay. So proton collision and a B quark comes, or a B hadron comes out. So first the B quark hadronizes to a B, and then it decays after that. Okay.
It is shifted on the XY direction. The vertex is shifted in the XY direction.
Exactly. If it were shifted in the Z direction directly, it would mean that the B is being produced very far forward, which really doesn't happen in the proton collisions, right? The Bs are produced with some PT. Well, I guess they don't have to be, but the Bs that we can see are produced with some PT. So that means transverse. They have some momentum transverse to the beam line, and they have this transverse decay length. That's a good question. Technically, it could happen that they could be along the beam. Exactly. The beam is small enough. If you look here in the notes, there's a picture of the beam, the collection of the beam vertices, and you can see that the beam in Y is much less than a millimeter, whereas in Z, it's about 10 centimeters. That's about 5 centimeters wide in this case. Okay. All right. Let me just say a word, because Matt touched on this morning, about how it is that you can get whatever efficiency you want from the B tagging. So he mentioned 70%, I just mentioned 40%. How can those two be at all the same thing? If you take the combined probability that the jet comes from the primary vertex, and you do this by multiplying together all the likelihoods for all the tracks that are in the jet, that each one of them came from the primary vertex, you get a probability that's very small for the B jets, so a very large negative log, and you get a relatively small probability for the charm jets, and for the light jets you get not often a very small probability. In other words, the light jets usually do come from the primary vertex. So if you were to try to decide that you wanted a very pure population of B jets, you might say, aha, I will choose to take all jets for which this negative log probability is greater than 10. Okay, so by doing that, I've effectively cut out a very large fraction of the light jets, a very large fraction of the charm jets, and what I have left are predominantly B jets. So this would correspond to a low efficiency on the B jets, and the reason is, what's the most likely decay length for a B? Think about an exponential distribution. It's actually 0. Okay, so more B jets have 0 decay length than anything else. And so that's reflected up here in the spike. So by cutting it very tightly on this parameter, you're throwing away a lot of the B jets along with a lot of the background. So it corresponds to a very low B jet efficiency. If instead you cut over here, where you are happy to just remove the light jets but maybe keep some of the charm jets, that's where those numbers come in that Matt showed today. A B jet efficiency around 0.7 still keeps about 15% of the charm jets. Okay, but in principle, you can dial wherever you like along here, and you can pick any B jet efficiency. That will give you a characteristic light jet rejection that he talked about. The light jet rejection he talked about today when he was talking about the fakes. I assume that his 1%, this is where we should talk about vocabulary, that 1% mean you were picking 1 out of 100 light jets. In other words, your rejection factor was 99%, right? So the rejection here means 1 out of this many. So it would be 1 out of 10 to the 2 for the case that he talked about. You reject 100 for every one you accept. Okay. I'm afraid we'll have to come back to the information about the triggering and the missing energy tomorrow, but that will be just fine. We're almost, I'm not an hour behind. Is Nadi still here? Okay. Just about 15 minutes behind. Okay, so we'll cover the rest of that tomorrow. Are there any questions, though, before you go? Yes, Michael.
Can you give us some sense of how, all this stuff has been done in some form of CDF zero. So can you give us some sense about how reliable these estimates are?
The estimates for
All these various efficiencies, so the jet energy reconstruction.
yeah. So the efficiencies that go into, for example, the fast simulation or something like that. So it turns out that the fast simulations are all tuned to the measured values at CDF and D0. Okay. We haven't had a chance to tune them from the measured values at Atlas and CMS yet, although that will come next. But in fact, PGS really is experimentalists helping out their theorist friends by parameterizing the efficiencies that are measured in some polynomial function and putting them in. So they should be exact to the sense that they can be decoupled, or the different dimensions of the function can be parameterized separately, ignoring any correlations, for example, between eta and PT, something like that. Okay.
I guess my question is in the nature of, with real data, how well do you establish, with what level of confidence do you expect to establish these kinds of efficiencies?
So the energy, you mean for efficiencies? You mean like B-tagging efficiencies? Okay. So it turns out that B-tagging efficiency is one of the hardest, and the reason is that the efficiency that I've shown here are in simulated events, where I take events that I know have BB bar, and then I calculate what fraction of them are selected by the algorithm. In the data, I don't really have an easy way of selecting BB bar or B-jets for a very clean sample, right? So one way we do it is we kind of play these taggers off against each other. At CDF and D0, what's done is to select jets which have electrons in them. One of the bullet points that I skipped over was, you know that you have a B jet if it's a semileptonic decay, for the reasons that Matt talked about earlier today. So B to C gives you a lepton. So the B decay to charm gives you this lepton, and you can tag that as being an indicator of B decay, not a perfect indicator. Once you've done that, you have an enriched B sample. And in fact, if you go back to those plots, it even says enriched B sample up there. So the real answer to your question is that the efficiencies are probably known at CDF and D0 to about 5% and not better. And there's hope that at LHC we can do better by using the B quarks from top events, of which we'll have a large sample. We'll know those are B jets. We'll know that'd be very clean. That's the hope. It's all a statistics game. Okay, great. I'll let you go. And if there are any other questions, you can find me at supper.